Believe it or not, we have the last speaker, or maybe fighter, if I'm looking here to the left, next to the stage, of today's contest. The speaker will represent the Institute of Molecular Biology and Biotechnology in Greece. Amazing. We will first see the video of the Institute, then I will pass the floor on to you.
The Institute of Molecular Biology and Biotechnology is one of the 10 institutes of the Foundation for Research and Technology, Hellas. It was founded in 1983 and is located in Heraklion, Crete. IMBB is one of the most prominent life science research institutions in Greece, with an outstanding record of achievements, aiming to promote scientific excellence. The Institute is pursuing a broad range of research topics and strives to develop innovative solutions to global challenges in today's society. It comprises 32 independent laboratories carrying out research in a diverse range of areas, from nanobiology to neuroscience, from plant to insect biology, and from developmental biology to translational medicine and vector-borne diseases. It has state-of-the-art facilities, particularly in bioimaging and gene targeting, and is committed to the highest standards in the education of young researchers. IMBB has been a member of EU Life since 2020.
We are happy to welcome researchers from all over the world to engage in research in a dynamic, inclusive, and supportive environment.
Now this gentleman standing next to me will be speaking about DNA, right? Tassos Pavlopoulos takes us into the embryonic development where genes and mechanics sculpt the shapes of life. Please, one more applause for Tassos. And let's try to connect with his colleagues in Heraklion. You have a great support at your institute in Greece, also here in Brno. So the floor is yours, Tassos.
You are about to find out that boxing and biology share many similarities. To start with, the polygonal shapes found in boxing rings are also pervasive in living organisms. In animal epithelia, the vast majority of cells are organized, are acquiring a hexagonal packing pattern following some basic physical principles. Other types of polygonal shapes, for example square or rectangular cells, are considered unstable high-energy configurations and are only found rarely. Nevertheless, there are these checkerboard-like square epithelia found across the animal kingdom, raising intriguing questions about the mechanisms that make them and stabilize them. We attack this question by combining light fluorescent microscopy with functional genetics and pharmacological approaches in crustacean model organisms. This shrimp, during its development, some cells forming the ectoderm are basically forming precise rows and columns of cells, and live imaging shows that during this formation, the cells start as hexagonal, then they shrink one of their edges to become pentagonal, and find another edge to become square, organized in this checkerboard-like grid. So the number of cell-cell contacts is regulated by the opposing forces of cell adhesion mediated by adherent junctions and cell contractility by the actin and myosin filaments at the apical surface of the cells. Just as actin and myosin power my muscle contractions during my punches, actomyosin contraction leads to the shrinkage of cell edges during cell shape changes and cell rearrangements. Therefore, we performed live imaging of myosin in developing embryos, and we found out that myosin was on fire, literally and metaphorically, exhibiting a highly dynamic pattern. We observed a directed flow of myosin from a loosely organized medial pool towards the shrinking cell edges, and finally the corners where the neighboring cells meet. So this myosin flow was reminiscent of a widely conserved process in biology known T1 transitions that change the relative position of cells at the local scale and reshape tissue proportions at the global scale. So myosin during T1 transition accumulates in particular junctions, in this case the vertical one. It brings the four cells into a pizza-like configuration and then resolves in the perpendicular orientation, creating a new cell junction. So unlike in canonical T1 transitions, those observed in the crustacean epithelium start normally. The cells come at this four-way vertex and then are stuck in this configuration that accumulates very high myosin. So to test the role of myosin in stabilizing those four-way vertices, we tried many gene knockouts. Unsuccessfully though. Therefore, we were left only with one thing, to try drugs. So we used drugs not only to boost the experimental throughput, but more importantly, to block the myosin activity. So this one, you will not see here, but you will see in the slide. So essentially, what we identified is that myosin blocks the four cells at this four-way vertex, and we would like to. This will be the. This will be shown in another fight, because in this fight, the winner is the one and only, the legend of Moravia, Pavlopoulos. Bravo, Manu.
Well, that was a great, friendly fight that marked the end of this wonderful event.